In this lesson, we're going to learn about net ionic equations. So if you remember from last lesson, we looked at molecular equations, which gave us a chemical reaction with all compounds and elements given by their formula, and then the states of each of those compounds and elements were given as well. So AQ meant aqueous or dissolved in water, S meant solid, G meant gas, and L meant liquid. So we're going to look at how we go from a molecular equation to a net ionic equation, which describes chemical reactions based on the role of dissociation, or gives us the overall reaction that is actually happening. And we'll see what that means in a moment. So for that chemical reaction we just looked at between lead nitrate and potassium iodide, the overall or net ionic equation there would be lead 2 plus 2I minus becoming PbI2. And this here is a solid, so it is going to precipitate out because it has a low solubility in water. So we're going to take a look at how we start with our overall chemical equation or molecular equation. So we have lead nitrate reacting with potassium iodide to create or produce lead iodide and potassium nitrate. So these two beakers are representing the same beaker at different points in time. So the first beaker is the reactants. So we have lead nitrate, and if it's dissolved in water, it dissociates or splits into its ions. So we have one lead ion and two nitrate ions when lead nitrate dissociates. So there's that. And then we have one potassium ion and one iodide ion for every potassium iodide, but I have two potassium iodide here for this reaction as it's balanced. So that means two potassium ions and two iodide ions. So at the very beginning, I have my two solutions and I mix them together. And so at the beginning, what I'm mixing together is a bunch of lead, nitrate, potassium, and iodide ions. And then as they are moving around and able to come in contact with one another, what is going to happen is the lead ions with two iodide ions, when they collide, they are going to make lead iodide. And lead iodide has a low solubility, and so that is going to precipitate out and be found at the bottom of the beaker as a solid. Potassium nitrate, on the other hand, because it is also aqueous, it will be dissolved in water. So as potassium and nitrate ions collide with one another, they are not going to stay attached because they will dissolve in water. So those nitrate and potassium ions are still just going to be found in solution. So what we can see here is that overall there is no difference between nitrate ions in the reactants side and nitrate ions in the product side. So both of them are found as ions dissociated in water. And the same thing with potassium ions. So we're going to take a look at our steps from moving from a molecular equation to a net ionic equation for a particular reaction. So to determine the net ionic equation, we're going to write the molecular equation, or the balanced chemical equation with the states. Then we're going to write what's called a total ionic equation, and that comes from breaking up anything that dissolves in water into the ions it would dissociate into. Anything that is not aqueous would stay as its molecular formula. And then from there we're going to write the net ionic equation by removing any spectator ions, and spectator ions are anything that stay the same in reactants and products. So they stay the same, they stay as the ions. There is no chemical change with those. So to go back to that example that we've already started with, lead 2 nitrate and potassium iodide. So we already have the molecular equation, which is the first step. So the second step then is to split this into the total ionic equation, which we get from taking anything that is aqueous and dissociating that. So anything aqueous and ionic, or aqueous and an acid, is going to dissociate. So lead 2 nitrate becomes lead 2+ ions dissolved in water, and then 2 nitrate ions dissolved in water. Potassium iodide, so I have 1 from each, but I have 2 potassium iodides, so 2 potassium ions dissolved in water, and 2 iodide ions dissolved in water. And that creates the precipitate lead iodide and 2 potassium ions dissolved in water and 2 nitrate ions also dissolved in water. So that is the total ionic equation. And then the next thing I'm going to do there before I get to my net ionic equation is I'm going to get rid of any of my spectator ions. So those things that do not change in that reaction. So they're the same in the reactants and the products and therefore are not involved in the reaction. So I have 2 nitrate ions in the reactants and in the products and 2 potassium ions. So nitrate and potassium ions here are spectator ions, which means overall there's no reaction happening with them. So that means I have lead and iodide ions, which will come together to form the solid lead 2 iodide. So that is my net ionic equation. So writing everything from the total ionic equation that was not a spectator ion. So let's look through an example that we do together from the start. So fluorine gas is bubbled through a solution of sodium chloride. Now this one we did see the molecular equation in a previous lesson. So fluorine diatomic and a gas. Sodium chloride was highly soluble, so aqueous. And fluorine is more reactive than chlorine, so it takes its place. And this is also highly soluble. And then chlorine gas. So that is my full balanced equation. So there's my molecular equation. I'm going to take the two things are aqueous and I'm going to show those dissociated in the total ionic equation. So 2 sodium ions, 2 chlorine ions, 2 sodium ions, 2 fluorine ions, and chlorine gas. So I have 2 sodium ions on either side of the equation, so those are spectator ions and nothing else. So my net ionic equation then is fluorine gas and 2 chloride ions react to produce 2 fluoride ions and chlorine gas. So sometimes there may be no spectator ions, so there's nothing that you are canceling out, and that would mean that your total and net ionic equations are the same. So once you create your total ionic equation, if there's no spectator ions, nothing to cancel out, then when you write your net, there's nothing that would be different from total. And then on the other hand, if everything is aqueous, everything would dissociate, and that would make everything a spectator ion, which means everything gets canceled out. So that means there's no reaction. This is something we didn't talk about in Unit 2 when we did double displacement reactions, is how do we determine if a reaction occurs or not. And if everything is aqueous, then everything will dissociate, which means there is no overall reaction. The ions in the reactants are going to be the exact same as the ions in the products, which means there actually are no products. So there is no difference because all ions are aqueous and dissolved in water, and there is no change that is happening. No signs of a chemical reaction there. All right, we'll do one more example. So this we'll do right from the very beginning. We haven't seen this. So nickel 2 chloride. So I have nickel and chlorine's a 1-, so I need 1 nickel. Nickel is a 2+, so I need 2 chlorine. And chlorine's over here. So most things are highly soluble in chlorine. Exceptions are not nickel, so that means it's highly soluble, so aqueous. that is going to react with sodium hydroxide. Sodium's a 1 plus, hydroxide's a 1 minus, so we have a 1-to-1 ratio there. Hydroxides, everything in group 1, which sodium is in group 1, highly soluble, so that is also aqueous. And double displacement reaction, so nickel pairs with hydroxide, sodium pairs with chlorine. Remember to always write your metal first. So I started here with sodium, and then to chlorine, nickel, and then to hydroxide. So nickel hydroxide, nickel was a 2 plus, hydroxide's a 1 minus, so as I crisscross I need 1 nickel and 2 hydroxide. Hydroxide is highly soluble with all of these. Nickel does not fall into that, and so it is low solubility with most things, and nickel would fall into that. And then the other is sodium chloride. And we know from before, but we can double check, so chlorine with most things, sodium is not an exception, so that is also aqueous. And I have 2 chlorine with nickel chloride, so I need a 2 here. That gives me 2 sodium, so I need that, and that will give me 2 hydroxide, which I have. So that is my molecular equation, which is the first step. The next step then is to dissociate anything that is aqueous. So I have nickel 2 plus ions, 2 chlorine ions, 2 sodium ions, and 2 hydroxide ions. And then I produce the precipitate nickel hydroxide and 2 sodium ions and 2 chlorine ions. So the next step there is to find any spectator ions. So there's 2 chlorine on either side, 2 sodium on either side. So those are my spectator ions. So what I'm left with then are nickel and hydroxide coming together to form the precipitate nickel hydroxide. So that is my net ionic equation. So this is the overall reaction that would happen when I take nickel chloride and add sodium hydroxide to it. So there would be nothing happening with the sodium and with the chlorine. Those would be dissolved ions in the water in the nickel chloride solution, and the sodium ions in the sodium hydroxide solution, and then in the end, as sodium chloride as a product, that is also aqueous, so we still have sodium and chlorine ions, which would just be dissolved in water. So that's what makes them spectator ions. There's no change happening with those. The whole time, sodium and chlorine ions are just dissolved in water. Whereas when nickel and 2 hydroxides collide, those are not soluble in water or have a very low solubility, so anything above the saturation point is going to precipitate out and form solid nickel hydroxide.